Again, a reminder that we're going to have our second midterm next Thursday, and it's going to cover everything since the first midterm, which is lecture 9, till today's lecture. Okay, so shortest passing weighted graphs are going to be covered. All right, we'll send out emails later. Okay, so last time we introduced the weighted graphs where edges have weights and shortest passing weighted graph, and we talked about an algorithm that were to solve the so-called single source shortest path, namely we want to compute the shortest path from a given source node. Okay, so the algorithm is called the Bellman-Ford algorithm. It can solve this problem in time complexity V times E. Okay, and it relies on operation called edge updates. Okay, it repeatedly perform this update operations. So the algorithm works, but it's not very efficient. V times E can be large. Okay, E can be V squared, so this can be V cubed algorithm. So today we're going to look at another algorithm called the Dijkstra algorithm. This algorithm is much more efficient than Bellman-Ford algorithm. However, the algorithm only works for graphs with positive edge weights. Okay, all right. So now let me first say that it works only for positive edge weights, but this is by far the most natural way, most common type of weighted graph in practice, because very often the weights of the edge carries meanings like distance, importance. So usually this is a positive number. Okay. Now the Dijkstra algorithm is going to have some similarity to the Bellman-Ford algorithm we introduced last time, in the sense that both of them will repeatedly perform this update operations to keep improving our shortest path estimate till we cannot improve anymore. Okay, the difference lies in that Dijkstra will perform this update operations more intelligently, okay, to remove redundancy. Okay, so in particular, if you remember, how does the Bellman-Ford algorithm works? Well, it's going to run in V iterations. Okay, in each of the V iteration, it's simply going to perform updates for all the E number of edges in your graph. Okay, so you do this E times. Okay, so it's actually runs in V minus 1 iteration, but almost V. Okay, so and then in the end, we guarantee after all of these updates, all the shortest paths will be captured. And the reason we only need the V minus 1 iterations was because the longest possible shortest path in terms of number of edges can have at most a V minus 1 number of edges, because they have to be simple if your graph doesn't have negative cycle. Okay, now if assume that all edge weights are positive, okay, then we can actually rule out paths more immediately instead of doing a lot of redundant updates. Okay, so here just one example. Let's consider this graph. Okay, let's say that so at the beginning only the node S has distance estimate 0. Okay, let's say we perform the first round of updates for all the edges, and after that, when we perform updates for this edge, we know that the U2 will receive an estimate, distance estimate of 2. Okay, and when we update this edge S to U1, then we find a better way to reach U1, and U1 will receive estimate distance 5. Okay, and it doesn't matter what are these edges at the beginning. When we run the updates, it depends on the order, we probably don't improve. However, now imagine, suppose I already know that this has estimate 2 and this has the estimate 5. Okay, is there still any need to perform the update for edge U1, U2? Okay, doesn't matter what this weight is. We see that, okay, we don't need to, okay, because this edge weight can be anything, but because it has to be positive. So I know that the path coming from U1 cannot be better than what I already have. Okay, so in a sense, there's no need to perform update on this edge U1, U2. Okay, so Bellman-Ford would still perform that update, which would give a lot of redundancy to this. Okay, so that's the idea. Okay, so here we're leveraging that the edge weights are positive. But the question is that in general, how do we use this to design a strategy so we can systematically still explore the graph and updates our shortest path estimates and without missing anything important, okay, while guaranteed to perform it more efficiently. Okay, so that's what we're going to see. All right. Okay. Now, on the high level, Dijkstra algorithm also bears similarity to the breadth-first search algorithm we described earlier. Okay. Now remember that what is the idea of a breadth-first search? In breadth-first search, we essentially say that okay, we do it greedily. Okay, we're going to starting from the source. We're first going to explore all the nodes that we can reach within one step. Okay, then we start to explore those nodes that one step away from the source and start to explore them, so we can reach all the we discover all the nodes that are 2 steps away, 2 edges away from the source, and so on. Okay, so essentially in BFS, for each node, we also maintain an estimate of shortest path to the source, although there the shortest path is measured as the number of edges you need from the source. Okay, and this estimate will be updated, and algorithm will explore the nodes in the BFS in a greedy manner in increasing distance to the source. Again, in the BFS, the distance was the number of edges. Okay, so we're going to do something similar in Dijkstra algorithm. Namely, we still will maintain the estimates of shortest path distance to the nodes, and we're still going to explore the nodes in a greedy manner. In other words, in increasing distance to the source. The difference is now we are going to, this distance is going to be the choose weighted shortest path distance to the source. Okay, so very similar to BFS, we're going to explore those nodes that are closer to the source first before we explore those nodes that are further away from the source first. Okay, so, and another guarantee that this algorithm would have is that by the time we start to explore a node, okay, the algorithm will be guaranteed to have already computed the correct shortest path distance from the source to this node. Okay, just like in BFS, I mean, when we start to explore a node, then that node actually we already know the number of edges needed to reach that node from the source. Okay, all right. So so here's a high level idea. Okay, suppose our source node is S. Okay, similar to BFS, as I mentioned, Dijkstra algorithm keeps track of estimated shortest path distance found so far. Okay, and we're going to use this u.estimate to store this current estimate shortest path distance. Okay, we also keep track of the shortest path distance themselves by remembering the predecessor along those estimate shortest paths. Okay, and at the beginning, all the nodes has this estimate distance to be infinity other than the source, which has a distance 0. Okay, and the algorithm will keep track of set C of correct nodes. In the set means that this set C are the nodes we already explored, and we have already computed their shortest path distance correctly. Okay, all right. And at every step, okay, we're going to grow the set C. We're going to find a node outside of this set of nodes we already computed the shortest path correctly. Okay, we're going to find a node outside of this set with the smallest estimated distance. Okay, and it turns out that that one has to be correct shortest path distance as well. Okay, and then we add it to C, namely now expand the set C by another node. Okay, and we also do some update estimate distance to all its neighbors to maintain this invariance. So this high level what the algorithm is doing. So we gradually grow a set of correct nodes that we know this distance correctly. Every time we find a new node which will guarantee that we know its shortest path distance, we add it and then updates all the shortest path estimates, and then we continue till in the end we collect all the find the shortest path distance to all of the nodes. Okay, so that's what the algorithm is going to do. All right, so before we talk about the algorithm here, just one example what I meant by that. Okay, so at any stage of the algorithm, let's say this is right now in the intermediate stage of the algorithm. Let's say we have already computed a set C, those are 3 nodes, S, U1, U2 here, that I circled here. Okay, so all of this right now, I computed their estimate distance already correct. Okay, and what do we do next? Now, from outside, and all the nodes also have some estimate of shortest path. Okay, now I want to pick another node that whose shortest path distance turned out to be correct. And the strategy I'm going to use is a greedy strategy. I look at the outside, so these are the nodes outside. C. So this node, we don't yet know what's the shortest path distance to them, okay? But among all these outside nodes, I'm going to pick the one greedily whose shortest path estimate right now is smallest. So this one doesn't have anything, that means it's infinity, okay? So this is 654, so U6 has the smallest estimate, okay? That means that I'm going to now pick U6, okay? And I'm going to include U6 into my set C. So now this is my set C, okay? But then from here, I'm going to explore U6 and update the shortest path distance estimate for other nodes. And I repeat, okay? Every time, then I pick the next one with the smallest estimate, then include into C, and I update explore that node and update the estimate to other nodes, okay? And repeat. Okay, so that's the idea of the algorithm. So we're going, starting from S, we're going to gradually grow who I can reach correctly, okay? And this is, again, if you think about the breadth first search, the idea is very similar. In breadth first search, starting from the source, you start to grow in terms of the nodes that you can reach, correct using shortest path distance. And also, the way that you grow this is that you're growing in increasing distance. Okay, the same will be true for the Dijkstra algorithm. Okay. So this is the high-level outline of the Dijkstra algorithm. This is not a real code because we're going to see there are things that are not really it's not really code. Now the idea is what I said at the beginning. Let's set up this estimate. Let me use a different color. So this is the, we're going to estimate the shortest path distance, okay? At the beginning, only the source has estimate 0. Everybody else at the beginning has infinity as their shortest path distance estimate, okay? We're going to also remember the predecessor for every node, which keep remembering what is the predecessor along the estimated shortest path to reach this node currently, okay? Same as a Bowman-Ford algorithm last time, okay? So now, the C is going to represent the set of C is going to be the set of nodes we explore. We know that we computed shortest path distance correctly. Okay, so C is the set that already visited, and I know that it got to their shortest path distance, okay? So at the beginning, C is empty, okay, because we don't yet know anything, okay? Now, what does the algorithm do? The algorithm says that, well, there's still nodes outside C, okay? There's still nodes that I haven't yet explored and find their shortest path distance, okay? What I'm going to do is that I'm going to find a node U from outside C with the smallest estimated distance so far, okay? This is basically a greedy choice. Okay, so I basically, every time I look at the nodes that I haven't yet explored, I haven't yet know their correct shortest path distance, I pick the one with the smallest estimated distance, okay? Then I add that to my set C, okay? And after that, I want to explore this node, okay? Now, how do I explore this node? I simply say that, okay, let's look at all the neighbors of node U, okay? So that you now pick the U, you already said that I'm going to add this to the set of, to the set C. Now you look at all the neighbors of U. For each of the neighbor, you basically perform an update to this edge to see that, okay, now that I pick the U, does this give me a better way to reach its neighbor V? Okay, so that's what this update is doing. Update is saying that through this edge, do you find a better way to reach V? Okay, so you update all these edges to see whether you can discover a better way to reach of any of its neighbor. That's it. This is how you, this is simply, this part is just to explore U. Okay, that's it. So in BFS, explore U is very easy. In BFS, I simply, from U, I look at all its neighbors. If it's not yet pending, it's still undiscovered, I discover it. That's it. I put it pending. That's it. Okay. So here we need to change the distance. We check whether we can find a better estimated distance. Okay, that's it. And in the end, I return the estimated shortest path distance and also predecessor. With predecessor, that gives you sufficient information to recover the shortest path distance, shortest path themselves. Okay, all right, questions? Okay, right. So, but note that this is not an implementation because we didn't really talk about how to do all the steps. Okay, but let's right now stay high level about what is the algorithm, and later we'll talk about its implementation. Okay. All right. So let's just go through an example of this algorithm. Okay, before we talk about its correctness. So let's say this is my input graph, and my source node is S. Okay. Now, I'm going to mark the estimate or shortest path distance here, and I'm also going to mark all the predecessor edges using red, okay? So at the beginning, everyone get an estimate of shortest path distance infinity, other than the source, okay? And we initialize the set C to be, at the beginning, it's empty, okay? And all the other nodes are here. These are all outside at the beginning. Okay, now the algorithm says that, okay, now from those nodes outside, let's pick one with smallest estimate, shortest path distance estimate. That clearly is C. So I'm going to first pick C, that's S, the source, because that's the only one. And then I need to explore this node, okay? So in the algorithm, now I need to explore that, or the neighbors of it. So I look at all the edges incident to S, okay? I look at SA, the edge, and then by updating this one, I discovered a better way to reach A. Okay, so by exploring S, I find a better way to reach A, and the way now A can be reached within distance 2. Okay, then I explore SB. Okay, and then let's assume that within the neighbor, for the neighbors of a node, we always explore in alphabetical order. Okay, so now explore edge SB. So I should put that this is edge that indicates a predecessor, okay, from S to A, that S is the predecessor of A. Then we explore the edge SB, and this discover a new way to reach B with distance 10. It's also better than before by performing update, and this gives us a better way to reach B, so S is a predecessor for B as well, okay? The same thing happened to C. When I update SC, this edge, perform update operation, I find a better way to reach C with distance 8 through this. 0 plus 8 is 8, okay? And this is my predecessor, okay? So this finished the stage 1. So after stage 1, what do I have? I have that the outside only have A, B, C, D. Only this are outside. So if I use green to represent C, so now this is C, okay? C contains S and everything else is is outside. And I have updated the shortest path estimate for some of the nodes. D is still remains infinity. Note that when I do this in this round, our algorithm doesn't update edge AD, doesn't update edge BD, because those are not yet relevant right now, okay? All right, then in the next iteration, what does algorithm do? It says, okay, now let's pick one. From outside, let's pick the node whose estimated distance is smallest. Okay, so from A, B, C, D, I need to pick the one whose estimated distance is smallest. And that's A, because the distance estimate is 2. So far, this one has the smallest. So we're going to include A, we're going to include A inside C, and outside is only B, C, D. Okay, so now I'm going to include this A inside C. That means that my outside, now it includes A and the S. Okay, all right. Now we now take A, we pick A, then now we need to explore A now. Okay, just like BFS, you now start to explore this node. Now, when we explore, that means I need to look at all its neighbors. In this case, it only has one neighbor, which is AD, okay? And when I do update AD, what happens? I found a better way to reach D, okay? The distance estimate now should be the distance estimate to A plus the edge weight 1, which is 2 plus 1, 3. So I get a better way to reach D in 3 distance, okay? 2 plus 1. This is just the perform after update operation. That also means that now the predecessor of D is A, okay? A doesn't have other neighbors, so there's nothing else to do, okay? So by exploring A, we only discovered D, nothing else happened, okay? Okay, so now the second round is over. Okay, then we continue. We say in the next stage, let's pick outside who has the smallest distance estimate. And it turned out that even though the B and C were discovered in stage 1, first iteration, but they're not going to be explored because right now the one with the smallest distance estimate is actually D. Okay, so in the next stage, I'm going to pick D. We're going to now take D and start to explore D, okay? So we remove D from outside and we include the B into outside, so into set C, okay? Now I need to explore neighbors of D, okay? So we look at it, D has only one neighbor, which is B. And when I perform update BD, what happens? Update BD says that I check the distance to D, which is 3 plus 1, and that's 4. And 4 is smaller than 10. So we discovered a better way to reach B with distance only 4. Okay? And because of that, we say, okay, now I found a better way. The predecessor of B is no longer S. The predecessor of B now is changed to be D. And the distance estimate to B become 4, okay? And D doesn't have other neighbor, that's it. There's nothing else to do, okay? So this is what we have after this stage. We continue. Now, in the next stage, we say, let's look at the remainder outside the nodes we haven't explored yet. What is the node with smallest distance estimate? Well, that is B, because B has distance estimate 4, while C has 8, okay? So we're now going to explore B, and we remove it from outside. So we're going to explore B, and the B has 2 edges. B has edges to C. When I do update, that means that from B, I have another path, which is 4 plus 6, that's 10. But 10 is bigger than 8, that's already there. So the update operation does nothing, because it says, okay, this new path I found through B is not better than what I found before. Okay, so there's nothing to do. So when I update edge BC, nothing happens. I have another neighbor, which is BS. Now, when I perform update BS, that means that I found a new way to reach S through the first reaching B plus 10. So that's 4 plus 10, that's 14. 14 clearly is worse than 0 we start with, so nothing happens, okay? So when here I perform 2 edge updates, but it doesn't get me any new distance estimate, nothing changes, okay? And then we are done, okay? So this is after, and of course we have to now include B also into our inside set C, okay? So there's only one left outside C, so next round, we remove C from outside, and outside become empty. So now we start to explore C, okay? So when we explore C, we do the same. So now everything is inside now, there's nothing outside. We explore C, that means I need to update these 2 edges. C has neighbor CB, but then doing CB give a distance which is 8 plus 4, 12 to B, which is worse, 8 plus 6, which is 14, which is worse than the distance to B already. So nothing happens. And CS, which is also not going to be any better, okay, nothing happens. Okay, so that's it. So that's the algorithm, and then we're done. So the final, what we return basically S return distance 0, A return distance 2, D return distance 3, B is distance 4, C is distance 8. And these red edges are predecessor along the shortest path that we returned. Okay, so for example, the shortest path from S to B is basically B go to its predecessor is D, and then AD and SA. In other words, it's S to A, A to D, D to B. That's the shortest path to B, following the predecessors. Okay, so that's the end of the algorithm. Okay, questions on how the algorithm runs? Right. Okay, so if there are no question, we're going to talk about the correctness of this algorithm.